Welcome to Statistical Mechanics. This is a module designed to give you further understanding of the fundamental principle of statistical mechanics in the chemical context. So let's continue with follow up with the concepts we introduced in the previous two lectures about probability and probability distributions, and let's try to put now these more into the context of chemistry. You should already know from the previous lectures what is a statistical mechanics, what is the relationship that it has with thermodynamics, and you already refreshed your mathematical knowledge on probability distributions, and some of the mathematical framework that we need to follow with the lectures in the days to come. Today we're going to talk about the Boltzmann distribution. So remember, we were saying that statistical mechanics is a bridge between the microscopic world of atoms and molecules and the macroscopic world where we have average properties like pressure or temperature. Well, within this framework, the Boltzmann distribution connects the energies of individual molecules with the energy of the bulk matter. And that makes the Boltzmann distribution one of the most important concepts in chemistry, because as we will see later on in the module, and as you will find in many other modules during your chemistry studies, the Boltzmann distribution is almost everywhere when you want to understand many chemical properties and its connection to the microscopic molecular world. So if we think about any bulk material, and here we are start with the example of liquid water, this is always composed by millions of molecules that are in continuous and random movement. As a consequence of this movement and interactions, these molecules are in different energy levels. And usually, we assume that those levels that are more populated are those with less energy. Now, the population of this level is a result of different contributions coming from the actual state in which each of the molecules are. And this contribution is coming from the vibration of the bonds and different components of the molecule, rotation, translation of the molecules throughout the space, as well as the electronic state of that molecule, where the electrons are in terms of their own energy levels. Now, this number of molecules in that form that configuration is called the population of this energy state. Now, as we increase the temperature, the population of the different energy levels change, and more molecules appear in the upper energy levels. At lower energy, most of our molecules are in lower energy levels. Therefore, these lower energy levels are more populated. As we increase the temperature, more molecules reach out to higher energy levels. There are more energy in the system because of the higher temperature, and they can reach to higher levels. This is very important because, as you will see in many other areas, that's the reason why we have chemical reactions, many other chemical processes happened because of this phenomenon. So if we actually count, in this case for just a few molecules, the number of molecules, that population of energy levels, we use this Ni, to refer to the energy level, and each of the energy levels have an energy EI. Now, as we are gonna see today, these two factors are connected also with the temperature through a formula which is indeed this exponential, that is what we will find in the Boltzmann distribution. So today's lecture is about finding this actual connection. So to get to the actual expression that connects the population of the energy levels with the temperature, let's first go through some definitions and key concepts that are needed to derivate the expression for the Boltzmann distribution. So first of all, we are considering that we have distinct and independent particles. What does it mean? It means that we can always tell which is which in our system. So molecule A, B, C, and D. We know where is A, where is B, and how they are moving around. We also assume that they interact with each other minimally. Let's say that they have enough energy to, let's say, interchange a little bit in the collision, but we are assuming there is no actual potential energy that attract each other. You are already familiar with this when we are talking, for instance, about ideal gases. So we say they are weakly coupled. Because of that, we can then define our total energy as the addition of the individual energies of each of our molecules in our system. We also assume that there is equal probability of configurations. This is called the principle of equal a priori probabilities. All possibilities for the distribution of energies are equally probable, and there is no bias towards any configuration. We also assume that there is conservation of number of molecules and energy. This is rather obvious, but still required. The number of particles and the total energy in our system is conserved. If we put this in terms of a mathematical expression, the addition of all the different populations that we have throughout our energy levels adds up to the total number of molecules, while multiplying these individual populations times the energy of that state gives us the total energy. Now, another one is configurations, the concept of configuration, sharing out the energy. At any instant, the distribution of particles among energy states may involve, let's say, n sub 0 with energy E sub 0, n1 with energy E1, n2 with energy E2, and so on and so forth. We call this instantaneous distribution the configuration of the system, such a way that we use this notation in which n sub 0, n sub 1, and n sub 2 gives the population that we have in each of these energy levels. Let's explain this a bit further. So this is, for instance, configuration in which all our molecules N are in state 0 with energy is E0. Therefore, if we have our energy level with for instance, 5 molecules that here I show in different colors, there is always one possible distribution, all of them in this energy level. There is a typo here. It's not E1, it should be E0, although we could do the same if it's for any other energy level. Now, imagine we have this other configuration in which 2 molecules are promoted to the second energy level, E1, and now we have other possibilities. Now, if we have 5 particles, again, we have 5 possibilities to choose what to put in the first. Let's say, imagine we look at the E1. We have 5 possibilities. The gray, blue, orange, yellow, or green particle could go to the energy level E1. If we choose, for instance, the gray, we have now 4 possibilities to choose which one goes again to E1 to constitute the 2 in our configuration. Remember, we are doing N-2, 2, 0, 0 configuration. Or for 5 particles would be the 3, 2, 0, 0 configuration. So in E1, there should be 2 particles. We already chose one, the gray one. Now we need to choose another one among these 4 possibilities. So imagine we choose the blue one. If we do that, that's the configuration we get. But we could have chosen the orange one and get this one, or the yellow, get this other one, or the green and get this 4th one. So for the case of choosing as first choice the gray, we have a total of 4 possibilities. If we would have chosen the blue, we would have had another 4. So in the end, what we have is 5 times 4 possibilities for our configuration. Meaning if we continue, in general, would be like n times n minus 1 possibilities. However, the actual configuration, which in E1 we have gray-blue, is equal to the one in which we have blue-gray. So then we need to divide this by 2 to really account for the total number of possibilities, which in this case is 10. So if you think about this, we are going from our initial case in which N000 gives one only possibility to one. The moment we put 2 particles in the first energy level, we have 10 possibilities. As you already know from the previous lectures, and we will continue discussing throughout today's lectures and others to come, this case with 10 possibilities is more likely to be found than one in which only one is possible. So this allows us now to define what we call statistical weight, or the weight of our configuration. It's closely connected to what we call multiplicity in the previous lectures when discussing probability. The number of ways in which a given configuration can be reached is what we call a statistical weight. It represents the probability that this configuration can be reached from among all other configurations by totally random means. Meaning, if our configurations has higher weight, means is more likely, more probable to be reached. That's what we said right before. The one with 10 possible configurations is has higher probability to be reached than the other one that has only one. So for a configuration in general like this one, we know from our previous discussion that the total number of possibilities would be n factorial. Remember, we already discussed and we are familiar with this exclamation funny sign. This is factorial. And then if we have, let's say, our three energy levels with where our n0 particles go to the E0 energy level, within that state, there are actually n0 factorial possibilities. Same happens for the other two. So for calculating the actual weight, the weight of the configuration is the total number n factorial divided by the product of the different factorials of the different populations of the levels. Now, the final concept to discuss before going forward is the predominant configuration. The predominant configuration, and we will go further in other lectures, is the configuration with the largest statistical weight. What we just said before, this configuration dominates the assembly and imposes on it its own characteristics. This is important because, as we said before in previous lectures, remember we said that the macroscopic observation of the properties of our system is the result of this average over an ensemble of different microstates, meaning that the configuration with largest statistical weight is the one which is the one that dominates and the one that we are going to observe as an ensemble in our macroscopic measurement or evaluation of the system. So, and now what? Well, with all these definitions and concepts, which we have here, we can now try to find what is the actual connection in between these variables. So remember, we said that we have a conservation of a number of particles and energy. This is the way we note the configuration, and this is our statistical weight. So today we are not going to go through the actual mathematical derivation. We can do this in class, but let me at least introduce some important operation we do with the statistical weight for the derivation of the Boltzmann distribution. We usually apply logarithms because it's more convenient. So basically, the logarithms of W, of statistical weight, can be expressed in these terms, and we can approximate it. That's why we do it, because we can approximate it using the so-called Stirling approximation. Basically, it's a mathematical trick that helps us to get rid of the factorials. And then we can work with logarithms, which is usually much easier than working with factorials. So we are going to leave it here. I just want you to know at this stage what is the Stirling approximation as a way to simplify factorials. And in principle, with what we have right now in front of you, you should be able to proceed till finding the expression for the Boltzmann distribution. Assuming we do that, and we take the time to do all the derivations, what we get is the following expression that we see here. This is the Boltzmann distribution. This beta parameter is actually 1 divided by kT, where T is the temperature and K is the Boltzmann constant. This is a universal constant with this value that we see here in units of energy per temperature. The reason why it has these units is because it is actually, if you look at the exponential expression, it is first multiplying the temperature and then is dividing the energy. And the exponential, and as you already know, should be dimensionless. So the energies of the Boltzmann constant are chosen in such a way that the exponential doesn't have any units, as it should be, to be able to operate with it. Now, remember what we learned about probability in the previous lecture. We said that the probability of event A, P sub A, is the number of times the event A happens, N sub A, divided by the total number of trials. And now look at the Boltzmann distribution. We have the number of particles or molecules, N sub I, divided by the total number of particles. So meaning what we have there is a probability. So if we do this over all the different energy levels, so we calculate the probability of each of these states, what we have is a probability distribution. Probability distribution, as we learned in the previous lecture, is this distribution of particles all over the different energy levels. So the important here is that if you look at it, on the left side, we have a probability distribution. And on the right side, you have the energy of the state and one single parameter, which is the one that changes, and is temperature. And this is the most important take-home message of today's lecture. The most probable population of state I, with N sub I particles and with energy E sub I, depends only on one parameter, which is the temperature. So this is, we got to the actual expression of the Boltzmann distribution, and then to summarize today's lecture, this is the most important concept you have to take. This is the expression for the Boltzmann distribution. Don't worry, because we will operate much more with it. We will work more on its physical meaning and how we use it then in chemistry. So we will have plenty of time to get familiar with it. Important for now, remember, was the value of beta, how it's connected to the Boltzmann constant and temperature, and how this most probable population is related to the temperature. And actually, if you think about the beginning of the lecture, we were saying that at lower temperatures, we have a certain distribution. At higher temperatures, we have another distribution. So basically, this distribution of particles over the energy levels, according to this Boltzmann distribution, depends only and exclusively in the temperature. And this is a very important concept to remember and key for many other properties and many other concepts that we will discuss in statistical mechanics and that you will learn also in chemistry. Thank you, and see you next lecture.